In this video, we want to retrace the steps of the characters in the film Cube to find out how they found the exit for the cube. And so I think that pretty early on in the film, say around 20 minutes in, they've discovered that primes mean traps. Or they think they've discovered that. Later on, they discover it's not just prime numbers, but powers of prime numbers lead to traps. I want to unpack that idea a little bit before we move on. And so I've set up this spreadsheet to help us consider how many numbers are eliminated. So 2 and 3 are prime, 4 is not, 5 is, 6 is not. We discussed this a little bit when we looked at Ramanujan and his theories. So let's think about if a number is prime. So 2 is prime and 3 is prime. And then we might consider whether this number divided by 2, is that an integer? So throughout these numbers, I'm just taking out all of the evens. It says it's not prime if it's divisible by 2. So now I've set up the spreadsheet so that the power of the numbers across the top, don't worry about that yet. The number itself is down the left-hand side. And right now I'm just trying to decide if it's prime or not. Or I might look at all the no's and delete them. So all the even numbers except for 2, I'm deleting. Now we only have the odd numbers left. Alright, so now that we've gotten rid of all the multiples of 2, I can get rid of all the multiples of 3. And so 9 is not prime because it's a multiple of 3. 15 is not prime because it's a multiple of 3. 21 is not prime because it's a multiple of 3. So again, I can pull out all the no's and delete them. So at this point, we've taken out all the multiples of 2, all the multiples of 3. 5 is our next prime number, so I could take out all my multiples of 5 next. So this knocks out 25, 35, 55. Those numbers are not prime. And then I get to my next prime number, 7. I can pull out all the multiples of 7. This is the point where I get rid of 49, 77, 91, and some of the other multiples of 7 that we hadn't already gotten rid of. The next prime number we reach is 11. So now I have a list of prime numbers and powers of prime numbers. So we'll come back to this in a moment, but the grand idea here is that if one of the numbers in this spreadsheet is one of the numbers in the room code, then there is a trap. So 101 is prime if it had a 101 in the number code for that room, then it would be a trap. 343 is not prime, but it is 7 to the third power. It's 7 cubed. And so here we have an example of a number that would have passed the prime test. It's not prime, but it is a power of a prime. It's 7 to the third power. So this room would be a trap. So that was the immediate concern that the characters in the film had, were how do we avoid the traps? And it turned out the answer to that was powers of prime numbers. The more complicated problem in this film, mathematical problem, was how do we find the way out? And it was described that the whole cube the outer shell was designed by Wirth, and it is 434 feet in each direction, the outer shell. And with some quick calculation, Levin determines that each individual room in the cube has dimensions 14 by 14 by 14. And so if you figure out how many 14-foot rooms can you actually fit inside the cube, you get a smaller cube inside of the sarcophagus that kind of looks like this. And you can ultimately fit 26 rooms. Now some of these spaces will be empty because we found out that the rooms have space inside to move around and follow certain paths through the cube. But there are 26 spaces for rooms in each direction. And so the question is, if I'm here, how can I figure out that I'm only 3 spaces away from the edge? And how can I figure out where I've been and where I'm going? There we introduce an idea in 3-dimensional geometry, which is say that this direction across is the x-axis. This direction forward and backwards is the y-axis. And then the vertical space up and down is your z-axis. Or in the film, Levin uses z, which is the sort of European way to say z. So at any rate, if we're in this room at the front, we're at the first position on the y-axis. Y is telling us back to front. We're in the third to the last position in x, and we are third down from the top in z. So this might be this sort of shaded in room might have the coordinates. Well, on the x-axis, it's the last one would be 26, so 25, 24. On the y-axis, forward and backward, we're actually in the first spot, so that would be the 1 spot for y. And z, it's third down. Of course, all this depends on, are you counting left to right, top to bottom, or sort of the other way around. But we're going to count, this is x is 1, this is x is 26. This front piece is y is 1, the back would be y is 26. The top layer is z equals 1, the bottom layer is z equals 26. The goal is to get outside the cube. The cube is 1 through 26 in each spot. And so once you get a 27, you know you're in this sort of layer on the outside, your bridge to outside the cube. How do we get this information from the information in the film? So one of the rooms in the film, when they discovered this, they were in room 517, 478, 565. So how do they figure out where they are? Well, she tells you you add them to get your position. So 5 plus 1 plus 7, that's 13. 4 plus 7 plus 8, that's 19. And 5 plus 6 plus 5, that's 16. So at the moment that they discovered this is how you measure your position in the cube, they're at 13 on the x-axis, so about halfway in, left to right. 19 on the y-axis, so 7 rooms away from that outer edge, which is what Levin says, we're 7 rooms from the edge. And so they're about halfway on the x, towards the back of y, and they're 16 down on z. So probably somewhere back in here in 3-dimensional space. Halfway across in x, most of the way back in y, and more than halfway down in z. So that's how you determine an individual position from the room numbers. But how do we factor in this moving points idea? And so around an hour and 10 minutes into the film, they discover, oh, the rooms are moving, the positions are moving, so this is only the starting position. How do we figure out how that works? We'll discuss that piece in a second video because it requires a little bit more computation. But right now I'd like to wrap up this idea of powers of primes. So Levin at one point starts freaking out, saying it's impossible to consider all the powers of primes, which is absolutely true. Factoring numbers and figuring out the factors of numbers is actually one of the most difficult computational problems that mathematicians and computer scientists are trying to work on. It's the foundation of modern cryptography. The only reason that any data encryption works is because factoring numbers is hard. So she's absolutely correct, but she's only dealing with 3-digit numbers, and there just aren't that many 3-digit numbers. If you look at these powers of primes, for the prime number 2, after you get to the 9th power, you're out of 3 digits. So up to 2 to the 9th power, you're at 512. That's 3 digits. So 512 would be a trap. But then we get to 4-digit numbers, so you don't even have to worry about that. Our rooms are encoded with 3-digit numbers only. Well, when x is 3, 729 is the last 3-digit power of 3. Everything else is too big. If we're only worried about 3-digit numbers encoding our rooms, then these are only the first 6 powers of 3 matter. For 5, only up to the 4th power is 3 digits. Once you get to the 5th power, you'll get into 4-digit numbers. For 7, we talked earlier about 7 cubed is 343. After that point, the numbers are too big, too many digits, more than 3 digits. 11 can only be squared, and we have a couple more numbers up to 31, which is prime. 31 squared is 961. So after that point, any prime numbers, their powers are more than 3 digits. So no other powers of primes will be 3 digits. So you have to consider all of the 1, 2, and 3-digit prime numbers, but these are the only powers of primes that would give us traps. How many numbers are there? There are only 25 powers of primes that have 1, 2, or 3 digits. So there's all of the 1, 2, and 3-digit prime numbers, which Levin was already comfortable figuring out if a 3-digit number was prime or not. And she was very upset about having to consider all the powers of primes, but there's only 25 of them. So they were in a time crunch and under extreme stress, of course, but if you thought about it a little longer, you'd realize there aren't that many powers of primes that are 3 digits or less. So after listing all the 1, 2, and 3-digit prime numbers, and then adding in these powers of primes that are 1, 2, or 3 digits, these are the only numbers that could constitute traps in the cube. So to recap where we're at, we now know every possible 1, 2, and 3-digit number that would show us a trap in the cube. It could either be prime, or it's on this list here highlighted in blue. And we know how to figure out our absolute starting position in the cube by adding the 3 digits in each 3-digit number to get our x, y, and z. And we know the edges are at 1 and 26 for each coordinate. In the second video, we'll talk about the movement of the rooms and the details of how that works, because it wasn't explained very thoroughly in the film, and so I want to make sure we understand that and can do a couple problems based on that in the quiz.